Welcome to this comprehensive training module on the operation of centrifugal pumps. This is Module 3-3, created by Rahul Srivastava, a chartered chemical engineer. Over the course of this presentation, we will cover everything you need to know about starting, operating, troubleshooting, and shutting down centrifugal pumps safely and effectively. Whether you're a new operator or looking to refresh your knowledge, this module will provide essential guidelines that apply across a wide range of industrial settings. Before we dive into the technical details, let us address the most important point of all. No one should attempt to start, operate, or shut down a centrifugal pump until they have been fully trained and have demonstrated competence. What may seem like a simple task can have serious consequences for the operator, the equipment, and the entire plant if performed incorrectly. Written procedures established by pump manufacturers and experienced plant personnel must always be followed. In this module, we will present general guidelines, but remember, site-specific procedures always take precedence. Before starting any pump, an operator must understand certain aspects of its installation. Questions such as whether static suction lift exists, what liquid is being pumped, and where it is being delivered should all be answered well before startup. Even though operators typically do not install pumps themselves, understanding the installation factors is valuable, especially if you're involved in commissioning a new pump. Let us walk through some of the key considerations that influence how a pump is installed and configured. When a new pump arrives at the plant, it undergoes careful inspection for any damage from shipping. This is an excellent opportunity for operators to begin familiarizing themselves with the equipment. Key questions to consider include the pump's purpose and installation location, whether it is single-stage or multi-stage, whether it uses mechanical seals, and how the bearing housing is lubricated. Operators should also identify how the pump will be driven and review all nameplate information and accompanying documentation. The answers to these questions build the foundation of equipment knowledge that every competent operator needs. During the physical installation of the pump, operators should observe as much as possible. Pay attention to how the pump is secured to its base to prevent future vibration problems. If an electric motor is being installed on site, watch the alignment process between the pump shaft and motor shaft. Note whether a flexible coupling is used to connect them. These observations help you understand the mechanical setup and will be valuable when troubleshooting issues later on. Once the electrical connections are made, several important details need your attention. Look for an indication on the pump casing showing the correct rotational direction. If the motor spins the pump backwards during the initial jog test, the electrician will need to correct the wiring. Take note of the motor speed, voltage rating, and other nameplate information. Locate the start and stop controls and determine whether the pump can be started locally, remotely from a control room, or both. Also identify where the main breaker for the pump power supply is located and whether automatic start and stop capability exists. Observing the piping installation is equally important. All connections, whether welded, screwed, or flanged, must be made without placing any strain on the pump body. The piping must be independently supported so the pump does not bear any of its weight, as this could lead to vibration, premature bearing wear, and seal damage. Notice what methods are used to accommodate thermal expansion and contraction of the piping, and verify that all valves are easily accessible for operation and maintenance. Now, let us look at the fittings installed in the piping system. Identify whether there is a suction valve at the pump, a valve in the discharge piping, and what types of valves are used. Are they quick opening or slow opening? Do they have rising spindles? Check for a check valve in the discharge piping and a strainer in the suction piping. Understanding all of these components is essential because they directly influence the procedures for starting, operating, and shutting down the pump. Instrumentation around the pump provides critical operational data. Check for pressure gauges on both the suction and discharge sides of the pump, as well as gauges on either side of the suction strainer. A high differential pressure across the strainer indicates it is becoming plugged. Identify the indicating lights at the pump controls and learn what each color signifies. Determine whether alarms for conditions like low suction pressure are local only or also displayed in the control room. Learn all of these details before you ever start a pump. If you encounter any fittings, devices, or instrumentation that you do not recognize, make a note of them and find out what they are before operating the pump. This knowledge could prevent serious consequences in the future. Also, if you identify any safety concerns that have not been addressed, such as a missing coupling guard, report them to your supervisor immediately. A coupling guard is a requirement, but it might have been overlooked. Operators may not need to know every step of pump installation, but a competent operator always has thorough knowledge of equipment before operating it. Now we move into pre-startup checks. Whether a pump has just been installed and commissioned or has been in service for years, certain checks must always be performed before starting. Never assume that any piece of equipment is ready to start without carefully inspecting it first. Because there are many variables to consider, the information presented here serves as a guideline only. There is absolutely no substitute for operator competence and adherence to plant-specific procedures. The very first step of any pre-startup check is to confirm you are at the correct location. This may sound obvious, but poor communication can easily lead to serious mistakes, such as starting the wrong pump. If you are told to start P1 and there are multiple pumps with that designation, always ask for clarification. Once you have confirmed you are at the right pump, survey the surrounding area. Are there people working nearby who should be notified? Is any maintenance in progress that could affect operation? Are there any unsafe conditions, such as a missing coupling guard? If you have any doubts, notify your supervisor. Here is an example of a pre-startup procedure for a pump handling non-toxic, non-flammable liquids. First, verify that the liquid supply is available. For instance, check that the supply vessel level is above the required minimum. Never assume liquid is available. Next, check bearing lubrication by verifying oil levels in the housing sight glasses. Ensure all drains are closed, including the casing drain and any strainer drains. Then, fully open the suction valve. These steps establish the basic conditions needed before the pump can be started. It is standard practice to start a centrifugal pump with the discharge valve closed. This limits the electric current drawn by the motor at startup, which protects and prolongs the motor's life. In our procedure, we also assume that a check valve is installed in the discharge piping immediately downstream of the pump before the discharge valve. If the discharge piping is already pressurized from other pumps feeding into the same system, the discharge valve could be opened before startup. However, for this procedure, we will start with the discharge valve closed. Ensuring that the pump casing is full of liquid, known as priming, is critically important. Starting a pump without liquid in the casing can damage packing or mechanical seals because they depend on the pumped liquid for cooling and lubrication. There are several methods for priming, depending on the piping configuration. When static suction head exists, as shown in the upcoming diagram, priming is accomplished by opening the vent valve at the top of the casing with the suction valve open. Liquid forces air out through the vent, and the vent valve is closed once liquid appears. Always verify that the suction pressure gauge reads normal pre-startup pressure. This diagram illustrates a typical piping arrangement where static suction head exists. You can see how the liquid supply vessel is positioned above the pump, providing natural gravitational pressure to fill the pump casing. Notice the suction valve, discharge valve, check valve, and the recirculation line. This configuration is one of the most common setups you'll encounter in the field. Understanding this arrangement is essential for grasping the priming and startup procedures we have been discussing. Some pumps require a recirculation or minimum flow line. This piping connects the discharge side of the pump, upstream of the discharge valve, back to the liquid source. When the flow rate through the pump drops below a specified minimum, perhaps because a downstream control valve is closing, the recirculation valve opens automatically. This additional flow path prevents the pump from overheating, which would occur if low flow continued for an extended period. Understanding how this system works is vital for safe pump operation. To summarize the recirculation concept, it is essential to maintain a minimum flow of liquid through a centrifugal pump at all times to prevent overheating of internal components. That is why the recirculation line is often called the minimum flow line. Additionally, when static suction lift exists, a foot valve in the suction piping prevents liquid from draining back into the supply vessel when the pump is not running. If the suction line remains full of liquid, the pump can be primed from an external source, as we will see in the next diagram. This diagram shows how a pump can be primed from an external source when static suction lift exists and a foot valve is installed. The external priming source fills the pump casing with liquid, displacing the air through the vent. Once liquid exits the vent valve is closed and the pump is ready for startup. This method is particularly useful when the normal suction path cannot provide the initial prime on its own. Here we see another priming method for centrifugal pumps operating with static suction lift. In this configuration, the pump is primed using liquid from the discharge piping, downstream of the discharge valve. This method leverages the already pressurized discharge system to fill the pump casing. Each priming method has its place depending on the specific piping arrangement and plant configuration, and operators should be familiar with the method used for each pump they operate. A less commonly used priming method involves a small priming pump, which may even be hand-operated. This priming pump exhausts air from the casing, creating a low-pressure environment inside. When the casing pressure drops sufficiently, atmospheric pressure acting on the liquid in the supply vessel pushes liquid up into the casing. Once liquid exits the casing vent, the vent is closed, the priming pump is stopped, and the centrifugal pump can be started. The next slide illustrates this configuration. This diagram illustrates the priming arrangement using a dedicated priming pump. You can see how the priming pump connects to the top of the centrifugal pump casing to evacuate air. This method is typically reserved for situations where other priming methods are not practical, but it is important to understand how it works in case you encounter this configuration in your plant. Two additional pre-startup items deserve attention. First, if the pump uses an external source of liquid for packing or mechanical seal cooling and lubrication, verify that this supply is flowing before you start the pump. Running seals without their cooling liquid can cause rapid damage. Second, ensure that all manually operated valves in the minimum flow line are open and that the automatic recirculation valve is operational. If the recirculation valve is pneumatically operated, confirm that the air supply to the valve actuator is available. Now we are ready to start the pump. When all pre-startup checks are complete, start the pump driver. If anything unusual occurs, such as severe vibration, shut the pump down immediately. If the pump is operating satisfactorily, slowly open the discharge valve to its fully open position. Opening the valve too quickly can cause a hydraulic shock to the piping system, potentially causing damage. Throughout this process, stay alert for any unusual sounds, vibration, or other abnormalities. If anything seems out of the ordinary or you have a safety concern, shut off the pump and report your findings immediately. After starting the pump and opening the discharge valve, observe the discharge pressure gauge and verify that it indicates normal operational pressure. This confirms the pump is generating the expected head. Also check carefully for leaks around the pump. Keep in mind that seals, especially new ones, may leak slightly more right after startup, but this should decrease within a few minutes. If packing is used to seal the shaft rather than mechanical seals, a small amount of visible leakage is actually expected and necessary for proper packing function. Let us now discuss routine operating checks. An operator should never assume that once a pump appears to be running normally, there is no need to return and check on it. In fact, routine checks should be more frequent for pumps that have recently been placed in service. These checks are neither time-consuming nor difficult, but they must be thorough, more than simply walking past a pump to confirm it is still running. At a minimum, listen for unusual noises. Experienced operators develop the ability to distinguish between normal operating sounds and abnormal ones. This skill comes with time and attention. Continuing with routine checks, review all instrumentation associated with the pump. Is discharge pressure normal? Is suction pressure within the expected range? Check additional instruments monitoring flow rate, temperatures, strainer differential pressure, and any other relevant variables. Remember that vibration can be transmitted from the pump through the attached piping, so unusual vibration heard at a distance may originate at the pump. Whenever possible, carefully feel the bearings to check for vibration and temperature. If bearing temperatures are above normal, verify lubrication immediately and monitor the temperature closely. Increasing temperature combined with bearing noise likely indicates imminent bearing failure. Report this immediately. Whether or not bearing temperatures appear elevated, always check bearing oil levels during routine rounds and add oil if necessary. Be careful not to overfill the reservoirs. For grease-lubricated bearings, follow established preventive maintenance schedules and avoid overgreasing. Inspect packing or seals for any excessive leakage and report it promptly. Ensure all problems are addressed immediately. If maintenance paperwork is required, submit it right away. For minor tasks within your qualifications, such as tightening a loose valve handwheel nut, go ahead and take care of them on the spot. Housekeeping is an important part of routine equipment checks. Keep the area around the pump clean and tidy, wipe up spilled oil, properly dispose of oil-soaked rags, and ensure nothing obstructs the motor cooling passages. Many motors have shaft-mounted cooling fans, and blocked cooling airflow can lead to motor overheating. If you are responsible for making logbook entries, do so as soon as possible after your checks. Log entries are a form of communication, so they must be clear, accurate, and timely. An important reminder: operators should not focus exclusively on equipment that is currently running or scheduled to run. Many pieces of equipment, especially those that can be started remotely, must be maintained in a ready-to-run state at all times for emergency situations. For standby pumps, this means keeping oil levels checked, suction valves open, casings primed where possible, and liquid supply availability confirmed, regardless of whether the pump is expected to run. Being prepared can make the difference in an emergency. Now, let us discuss how to regulate the output from centrifugal pumps. In some cases, pumps are driven by variable speed motors, and flow rate is controlled by adjusting motor speed. However, variable speed drivers are relatively uncommon and expensive. The most common method is throttling a valve on the discharge side of the pump. For example, an automatically operated valve at the inlet of a destination vessel might control liquid level in that vessel. One critical rule to remember: pump output must never be controlled by adjusting flow on the suction side. Doing so could starve the pump or cause cavitation, leading to serious damage. All suction side valves must remain fully open during operation. When it is time to stop the pump for a relatively short period, the procedure is straightforward. For a motor-driven centrifugal pump, it is generally correct practice to close the discharge valve while the pump is still running. If the pump has a minimum flow line, liquid will continue to circulate through the pump even with the discharge valve closed. If there is no minimum flow line, closing the discharge valve before stopping is still acceptable, provided the motor is stopped shortly thereafter. Importantly, with the discharge valve fully closed, a centrifugal pump will not develop enough pressure to rupture the casing or piping. This applies specifically to centrifugal pumps, not all pump types. After the discharge valve is closed, the pump driver can be stopped, usually by pressing a button or turning a switch at the pump. A critical safety point: never stop a motor by opening the main breaker, as this involves dangerously high voltages. Motor control circuits operate at much safer, lower voltages. In many cases, these two steps, closing the discharge valve and stopping the driver, complete the shutdown process. Typically, the suction valve is left open and the casing is left full of liquid, keeping the pump in a state that allows it to be restarted quickly if needed. Troubleshooting is a valuable skill that operators should continuously develop. Many problems arise during pump startup, operation, and shutdown. The ability to diagnose issues and implement corrections requires thorough knowledge of equipment construction and operation, combined with common sense. In the following slides, we will examine some of the most common pump problems, along with suggested remedies. In every case, we assume that the equipment was correctly commissioned and that pre-startup checks were completed properly. If the pump will not start and it is driven by an electric motor, the most likely cause is that power is not available. First, confirm you are using the correct operating switch for that specific pump. Verify that the main breaker is closed, meaning in the on position, and check whether it is tripped. If the breaker needs resetting, do so. If power appears to be available, consider other possibilities. Some large pumps have interlocks or permissives that prevent startup. For example, a position switch on the suction valve that requires it to be fully open, or a level switch in the supply vessel that prevents startup when liquid is too low. Operators should know all startup permissives for their pumps. If you have checked all the obvious reasons and the pump still will not start, it is time to seek assistance. A more experienced operator may be able to offer suggestions. If that does not resolve the issue, seek the help of a qualified electrician. There is no shame in asking for help. In fact, knowing when to escalate a problem is a mark of a competent operator. When a pump starts but the motor trips immediately, meaning it shuts down automatically, the likely cause is excessive electrical current draw that could damage the motor. While resetting the breaker will allow the motor to restart, the trip will probably occur again, so it is crucial to find the root cause first. Check for mechanical problems that might restrict free shaft movement. Look for obvious physical damage such as a bent shaft or anything tangled around the shaft, like a rag that was used to clean up spilled oil. Continuing with the motor trip issue, consider whether something might have been left inside the pump casing after routine maintenance. Before physically inspecting any part of the pump, always ensure the power is off for your personal safety. Remember that some pumps can be started remotely or automatically, so simply pressing the local stop button may not be sufficient. If you cannot identify an obvious cause for the tripping, seek help from a qualified electrician rather than repeatedly resetting the breaker. If the motor trips while the pump is already running, several causes should be investigated. Internal damage, such as a bent shaft or excessive misalignment between the motor and pump shafts, could be responsible. Another common cause is packing that is too tight, creating excessive resistance to rotation and forcing the motor to draw more current. Check for adequate leakage along the shaft. Remember, some leakage at the packing is normal and necessary. Further investigating a motor trip during operation. Depending on the circumstances, you may reset the breaker and restart the pump after correcting an apparent problem. However, if the motor trips again, you will need assistance from an electrician or maintenance personnel. Another possibility to consider is that the pump is moving more liquid than intended. If liquid is flowing to the normal destination and also unnecessarily through the recirculation line due to a defective valve, the increased total flow could cause the motor to draw excessive current. Check the operation of the recirculation valve. Loss of prime is a serious issue that can occur both before and during pump operation. If the pump cannot maintain prime before startup and static suction lift exists, the foot valve in the suction piping is likely defective, allowing liquid to drain back into the supply vessel. A leak in the suction piping, perhaps at a flanged connection, could also be the cause. After startup, loss of prime manifests as erratic discharge pressure and flow rate. The pump may sound noisier than usual and vibration may be present. The pump is being starved of liquid. When investigating loss of prime, start with the simplest explanation. The liquid supply vessel may be empty. If static suction lift exists and the vessel is not empty but the level is too low, the pump may not be capable of the required lift. Verify that the level is adequate. A clogged suction strainer at the pump inlet could also restrict liquid flow. If that is the case, the strainer must be cleaned. Additionally, remember that the pump must create a vacuum in the casing when operating with static suction lift. If air is being drawn into the casing along the shaft, this vacuum cannot be achieved. Ensure that liquid is available to the seals. There are additional situations that can cause loss of prime. If the liquid supply vessel contains a mixture of liquid and gas, for example, water and air, the air entering the pump can cause prime to be lost. Verify that the suction piping is properly submerged in the supply vessel. Environmental factors can also play a role. If the pump is located outdoors or in a very hot environment, liquid could be vaporizing inside the casing. Solutions might include insulating the pump or providing shade to protect it from direct sunlight. When discharge pressure is lower than normal, liquid flow rate will inevitably decrease. The problem often originates on the suction side of the pump, so check for liquid starvation using the methods we discussed earlier. If the pump uses a variable speed driver, verify that the impeller is rotating at the correct speed. A driver running too slowly will naturally produce lower pressure and reduced flow. Continuing with low discharge pressure, consider whether conditions at the destination vessel have changed. If the pressure in that vessel has increased, flow rate will decrease due to the increased head the pump must work against. If this pressure increase is abnormal, the problem lies downstream, not with the pump. There is also the possibility of internal component damage. Repeated or prolonged cavitation can cause severe impeller damage, and worn wear rings can allow liquid to leak from the high-pressure area back to the impeller inlet, reducing output. Only an internal inspection can confirm these issues. When bearing temperatures begin to rise above normal, act immediately because the problem can escalate very quickly. Start by verifying that bearing lubrication is satisfactory. Check oil levels in the bearing housings. Larger bearing housings may have internal cooling water coils. If so, verify cooling water flow and oil temperature. Check whether water has leaked into the lubricating oil or if the oil has been contaminated with any foreign matter. Pump vibration can also drive bearing temperature increases, so investigate and address any vibration issues as well. Excessive noise and vibration require immediate operator action. Several common causes include damaged pump bearings. If bearing temperature has been climbing and vibration was already detected, the situation has worsened and the pump must be taken out of service for repair. The pump could be starved of liquid, as we discussed earlier. Cavitation may be occurring inside the pump. If static suction lift exists, verify that liquid is properly entering the pump. If static suction head exists, confirm that it is adequate for the pump's requirements. Before concluding that the vibration originates within the pump itself, check external factors. An insecurely anchored baseplate can cause vibration from pump or piping movement. Check the baseplate bolts and verify all piping is secure and not placing unnecessary weight on the pump. Misalignment between the pump shaft and driver shaft is another common cause that may be detectable through careful observation. Internal mechanical damage, such as a bent shaft or worn impeller, will require an internal inspection to confirm. 2 more causes of excessive noise and vibration to consider. If there is no strainer at the pump inlet, a foreign object may be attempting to enter the casing. A large object will cause erratic discharge pressure and flow along with noticeable noise and vibration. The pump must be shut down for internal inspection. Additionally, if the pump uses a variable speed driver, the impeller could simply be rotating too fast, causing vibration. Check the driver operation and speed settings. If the pump temperature is significantly higher than normal but no other symptoms like vibration are present, the most likely cause is insufficient liquid flow through the pump. Check whether flow to the destination vessel is low and verify that the recirculation valve is open to maintain minimum flow, as we discussed earlier. Also consider whether the pump needs protection from external heat sources, such as direct sunlight. As with all plant equipment, when you are uncertain about a situation, always ask for assistance rather than guessing. This concludes our training module on the operation of centrifugal pumps. We have covered the complete life cycle of pump operation, from installation awareness and pre-startup checks, through starting procedures and routine operating checks, to regulating output, shutdown procedures, and troubleshooting common problems. Remember, the most important takeaways are: always follow established plant procedures, never operate equipment you have not been trained on, and never hesitate to seek assistance when something seems wrong. Thank you for completing this module, and stay safe in your operations.